Well, we've been modeling, a fairly simple example of an entity that moves around in a flat two-dimensional space. This is, as implied by some of the names, this is the simplest way one can model this kind of thing. I have discovered over time that, to my surprise, it's actually this constant rate of movement is actually a remarkably robust approach, and can model lots of things that you might not think of, especially when you just sort of fancy it up a bit. So I've asked you all to just kind of fancy up this simplest, crudest one that I presented in class to something that's going to be a little bit more capable. And what we're going to talk about today, after I give like a little numerical example of, and we'll see what that's about, is the next thing that generally comes to mind is, well, okay, this event stuff, hopefully at this point you see that it works for modeling movement. We've also seen that because of that implicit state, the location being computed using the equation of motion, that the particle's location at any point in time can be identified. And just sort of right off the bat, that's something that, as I explained, time step models simply can't do, for the simple fact that in time step models, there's no such thing as an arbitrary time. Times are only increments of, or multiples of the time step. Okay, so so the next thing you think of, well, what about detection? What if I have my entity that's moving from one place to the next, and then in the meantime, in between, it either gets detected by somebody else or it detects somebody else. And of course, that might change its actual behavior. Again, we won't take it all the way to that. We're gonna stop here at just the detection part, but today I'm going to start looking at how we can capture that detection thing. And specifically, it has to do with modeling a sensor that just has a simple type of range. And then there are kind of two key events, which are when a target enters the range and a target exits the range. And we'll see what that's about. But first, the numerical example has to do with one of the things that is fairly straightforward to do in code, but one has to validate or verify, at least, that the code is doing it correctly. And so in order to do that, you need to know what the answer should be. The trickiest part of the whole thing is figuring out what the velocity is. The whole key to this is having a certain velocity. So between the velocity and where the thing starts and when it starts, then you can figure out exactly where it is all of the time. But what is the velocity, and is the model doing it correctly? So let's just look at a simple numerical example. So supposing we have a mover and it's located just arbitrarily at coordinates 20 minus 30. And at time 0, it starts moving to a destination, the double destination. Okay. Oh boy, that was only need one destination. And we'll pick the destination as minus 1050, at a speed of 30. Okay, so the three things that we need to kind of verify, or the things I'd like to verify, are, first of all, what is the velocity of the mover during the move? Second is, when does the mover actually arrive at the destination? And then finally, just as kind of an interim thing, assuming it takes at least 2 time units, what is the mover's location at time 2? So the idea is that in order to verify that our implementation is doing it correctly, we need to know the answer to this. In other words, when you write the code, and run it, and you look at the numbers and you say, well, okay, I think that looks okay, but that's not quite good enough. We need to know that it's okay. Okay, so in order to know that it's okay, we need to be able to compute all these things offline by hand. And of course, computing them offline by hand can be, subject to its own issues. So, so let's look at that. Let's kind of look at this. Okay, so let's look at the velocity. So remember, how do we do the velocity? Remember that the way we were modeling this, so the D is the destination, X naught is the start move time, is the place that we last stopped. So the first step is to find the vector between our starting location and the destination. And to do that, we subtract our location, our last stop location from the destination. So that this will give us a vector in the right direction. And that's what we're after. Simply, again, now none of this is rocket science. It's all very, very straightforward math, but it requires some due diligence. And if you're like me, it's kind of easy to make mistakes. So, okay, so 10, 50 minus 20 minus 30, this is where the potential for mistakes come in. So we have a minus 10 minus 20, and so that's minus 30. And then we have 50 minus a minus 30, and so minus two negatives make a positive, and so we get 80. So it reminds me of supposedly a high school teacher was talking about how, we have two negatives. Two negatives can make a positive, but is it ever, possible that two positives can make a negative? And he said, I don't think that that's possible. And so one wise ass student in the back said, yeah, right. Anyway, okay, so here we have a vector in the right direction. That's kind of the key. But we want a vector in that direction with the magnitude of the speed. So to do that, we first turn it into a unit vector. To turn into a unit vector, we need to determine the magnitude. And so the magnitude, which is located, we're going to note with these double bars, hopefully you're familiar with that notation. If you're not, then, well, you are now. Euclidean distance. So what that does is that takes the difference, squares the components, the coordinates, and adds them up and takes the square root. Okay, so we have minus 30 squared plus 80 squared, so that's 900. Again, minus squared is always a positive. 80 squared is 6,400. And add them up, it's the square root of 7,300. And then we can actually pull the 10 out, because square root of 100 is 10. So the magnitude of the vector from our last stop location to our destination is 10 times the square root of 73. Okay, so now we have all the information to compute our velocity. So that's the difference vector. Let me get rid of all this nonsense here. Okay, so we have the difference vector divided by the distance. And so this is a unit vector in the right direction. We multiply it by our speed. And now we have a vector in the right direction at the right speed, and that's what velocity is. So now we just plug in. Here's our difference, minus 3080 over 10 root 73 times 30. And then when we multiply all that out, we get minus 90 over root 73, 240 over root 73, which is approximately minus 10.5 something and 28 point whatever. Okay, one important thing to notice here is that when you're doing a calculation like this that involves some rounding, it is important to carry as many decimal places as you can until the very end. In other words, you don't round off until the very end. See, if you round off here with this number, then you're going to produce inaccuracies. Okay, it's best to carry things all the way. So this answer, and when it comes, if I ever ask a numerical question and you give an answer like this, that is 100% acceptable. In fact, this is more exact than this is only approximate. This is exact. Okay. But just in general, whenever you're doing any kind of numerical calculations, always carry out as, ideally to infinitely many decimal places. In other words, the square root of 73, that's kind of the problematic quantity here. But as long as we keep it in this radical form, then this is exact. Square root of 73 as represented here is exactly what it is. Now, if I want to know, okay, it's hard to tell exactly what that value is. And so at this point, we can kind of convert it numerically with a, spreadsheets can be useful for carrying out these kinds of calculations. Just a simple calculator is really all that's needed. Okay, so we have our velocity, either exactly or approximately. And then kind of in the process, we got the, once we had our distance, then we have our travel time. Our travel time is the distance over speed. So since we're traveling in a straight shot, we don't have to worry so much about velocity. We're going to be traveling this distance at this speed. And again, just as we did here, carry it out to the last decimal place, to the infinite decimal places ideally, and then round it off to the last minute. So this says it'll take like 2.8 some time units. And then which says, okay, in between, now can we identify where the mover is going to be at time 2, which should be in between this somewhere. So what we do is we have this equation, which is where we stopped last, plus the elapsed time, which is our current time minus when we started. Okay, here we're starting at 0, just to make it simple, times the velocity. And so x, now this x is a function of t now. So at time 2, we simply plug 2 into this equation, along with the other information. So this is important to plug in the right things. So remember, our x naught was this value right here, 20 minus 30. We have our velocity here. So where do we get that? That was from here. And then the difference in time. So we have a time of 2, and we started at a time of 0. So that's what this piece is. And when you multiply that out, we get, again, to infinite precision, 20 minus 180 over root 73, and minus 30 plus 480 over root 73. And then when you put that into a calculator or whatever, it comes out to be this value. Okay, so now, and of course, you should always check my math on this, but now let's take a look at whether or not that that matched what we had done with our simpler. Now, can you see my NetBeans here? I hope you can. Okay. So, and you can pull this if you. So, in order to verify this, we can get our simplest mover, again, that we did in class. You don't even need the fancy one that I've asked you to do. Our simplest mover, together with our simplest path mover manager, are enough to verify whether or not these numbers are okay. Now, Java can't do these square root things, but nevertheless, we can do the numerical one. Okay, so our initial location, 20 minus 30, is that's what we had there, yeah. Our maximum speed is 30 that we had there, so we can create an instantiated an initial mover, a simplest mover with that location and that max speed. And then just to verify it's there, I'll print out the param string for that. And now for a simplest path, for us just using the simplest path mover manager, I just need to give it one waypoint, which is our destination, minus 1050. Okay, and then print that just to make sure that that's working. As is our wont, we have each listening to the other. And we'll use a simple property dumper just to kind of see where everybody is. And then let's, just to make sure that nothing bad happens, we'll stop after one end move and run in verbose mode. So this is how we can, again, what are we doing? We're double checking to see whether or not these values are okay. Oops. So let's, all right, so let's run this and see what we can find here. So double check that our simplest mover is our initial location, maximum speed 30. Our path mover manager just has one waypoint, which is our destination. And so we run. So the first is the run. This is the run for the simplest mover. So start move time is 0, last stop location, our destination not a number, and our velocity is 0. We haven't started moving yet. Okay, so now our current event for the simplest path mover manager, okay, remember it starts, its next index is -1, so that when we click it up, it goes to 0, and its next waypoint is undefined. But it schedules our next waypoint. So that's, and that's why, because start on run was set to true. If start on run was not set to true, it wouldn't even do that. Okay, so now next waypoint occurs, our next index goes to 0. Our next waypoint is now our destination, and then it schedules our move to at that destination. So now move to says, okay, now I have a new destination and I'll start moving there. So now my start move time, goes from 0 to 0. I mean, that's, but okay, so, but here's our first check. So here's our velocity, minus 10.5 something, 28.0. And oops. Okay, so what did we have? We had minus 10.5337, whatever, and 28 point whatever. And that's what we got. Out to whatever. Okay, so the velocity is being correctly implemented in our simplest mover. And then the second thing we can check is the end time, which is 2.8480. And that's kind of what we had here. Okay, so now what about the location at time 2? That's actually they kind of left that out here, and that was on the to-do list here. So how can we kind of do that? That's where that little pinger thing comes in. So if I instantiate one of these pingers, the idea is I'm going to do a pinger, I'm going to have it ping at time 2, and then see where the thing is. And remember, with a pinger, we give it a, we give it actually an arbitrary object, and then a ping time, and I'll give it a ping time of 2.0. And just to emphasize that. I'll print it out. And what else do we, okay, so I want it to fire the property change. When it fires the property change, I want to see it. Okay, so what I'm looking for is I'm looking for where is the mover at time 2.0. And I'll be able to tell that with this pinger. So let's just kind of go through, verify that, okay, our pinger got our simple mover and the ping time was 2. Okay, run. Okay, next waypoint. And then there's the first ping here. Okay, the first ping turn is at time 0. And then at time 0, the mover is at its original location and a velocity of 0 because it hasn't had the move to event yet. Okay, so now it has the move to event. We have the start move. And then the next event is the ping at time 2. Okay, so here's the ping at time 2. And what I'm looking at is, here's my simplest mover. Remember, the first item here is its location. And then the second is the velocity. So it still has the right velocity. And the question is, its location is like 1.067 something and minus 1.067 and 26.179 something. And that is at least what we got here. Okay, so the idea is that we have verified at least that the velocity and the movement and the current location as computed by the get current location method seems to be working because it matches what we computed by hand. And the difference, the reason why this is a reasonable way to go is because when we implemented it in the code, we didn't put these numbers didn't exist anywhere. We were just using the equations that we had, the various mathematical expressions. And so this is verifying that we indeed had done that correctly. It is far too easy to do it incorrectly. It's actually even easier to kind of mess up the hand calculations, which is why it's always valuable to have something where we can kind of test that out. Okay, so this is something that, again, to make sure that you have the information necessary to verify your code. And the thing about the reason why we run in verbose mode like this is because when debugging these discrete event models, this is very much what we need in addition to the debugger. The debugger is a very useful tool, but it doesn't necessarily help us when it comes to making sure that our events are working properly. And the events working properly are simply a matter of, do the right state transitions happen? And are the right events being scheduled or possibly canceled? So how do we verify that? Well, this verbose mode with the simple property dumper is really the most effective way to do that. It can be a little bit tedious, but if, in looking at some of the various programs that I've tortured you with this quarter, I mean, a lot of times running it in verbose mode like this to really identify what was going on would have been very helpful. Okay. So now that takes us to this idea of modeling detection. Now, as is per usual, we're going to start with the simplest case. There are actually several reasons for this. Why I always start with the simplest case regardless. One of which is it's generally going to be the easiest. And it's kind of like, you know, when you want to pick off the low-hanging fruit, and the simplest case is going to be the low-hanging fruit. That's one thing. The second is what I found in doing this. A lot of times you get some insights into what is going on with the problem when you do a simpler version rather than trying to tackle the most complicated version. And the third reason why this is a useful thing is that if for some reason you can't do the simplest case, if for some reason the simplest case just doesn't work out and you're stuck, then there's absolutely no hope for doing the complex case. In other words, if you can't do the simple version, then there's just no hope for the fancy version. So you might as well just kind of give up. Now, everything I throw at you here is doable, so don't give up on this. But sometimes, you know, there are some problems for which it's not clear whether the approach is going to work or not. Okay, so simplest possible case. So we have a sensor. We're gonna just put it at the origin. It's going to have a maximum range of, I'll call it R for range, and it's just going to kind of sit there. And we'll see a picture of this in just a second. So at time 0, we're going to have a mover, and it's going to schedule a start move event and culminating in an end move event. So that's our basic maneuver for the mover: a start move and an end move. Okay, so again, simplest case, kind of, or a canonical case. So the mover, let's say the mover starts outside of the sensor's maximum range. These are the questions that we need to answer if we're going to be able to model the ability of the sensor to detect the mover. So first of all, does the mover enter the sensor's range? In other words, you know, if I think of something like a radar or just even somebody looking around, there are some things that are outside the range and sort of some things that can typically come into the range. So one, does it enter the range at all? If so, then when and where? Those are things that are, if we're going to have a simulation model that captures these things, we need to know, you know, when and where. That's kind of the key. And then if that's the case and it sort of keeps moving, does the mover, does it eventually exit the range? And if so, when and where? And then on top of that, we have related questions, which we won't get into today, but we'll deal with shortly. When, if at all, does the sensor actually detect the mover? So as you may guess, the mover in question is going to be the target. That's something that the sensor is trying to detect. And then if that's the case, then at some point, when does it undetect the target? So when I say detect, I mean that should obviously brings, you know, convey a picture in your mind. And then undetect is just, you know, well, yeah, you know, we've all seen sort of air disaster things where the traffic controller says, oh, you know, we lost radar, you know, the plane fell off the radar here. So, well, under what conditions can that happen? Well, now the ones we're going to deal with is if the target just keeps going through and then eventually exits the range. And once a target is out of the range of the sensor, then there's no chance for the sensor to actually know where the thing is. You know, because, you know, how do sensors work? They work by exchanging energy with the target. And then beyond a certain distance, there's just the inability to do that at a level which you can detect. Okay, so now what does this look like? So here's our, I call this a canonical sequence, because in a way, this is kind of how what's just been described. That is, we have a target that starts outside the range. It has, so here's its say it has a destination that's over here. And so we're gonna have a start move event and an end move event. That's all we have so far. And the question that may have come up, and either implicitly in your minds or explicitly, is, well, what if something happens in between? Well, here are some things that can happen in between. First, again, if you look at the green dots, so here's our sensor. What this circle is that's its maximum range. And as you're well aware, many sensors, especially radar and other types of things, they will typically have a sometimes not a circular, but kind of a weird shape to their footprint. Again, we're doing the simplest version of this. It turns out, yes, we can model different shapes of footprints. It's just a bit more complicated. It's just easiest to do it this way to start with. It's the simplest. Again, if the footprint of the sensor is an issue, that's something that actually can be addressed. We just won't address it here. All right, okay, so here are the potential for intervening events. So one is as long as the target is outside the range of the sensor, then there's just no chance of it detecting it at all. But then at some point, it's going to kind of step into the sensor's wheelhouse. And so all we're going to say is, okay, at this point, from this point on, there's a chance, there's a potential of the sensor detecting the target. And then just concentrating on the green dots. At some point later, if the target just keeps moving and nothing happens to it, it'll eventually move out. So once this exit range occurs, then there'll be, again, no chance to have direct contact with that target. Okay, so now the question is, given that we are not doing things in a time step way. Remember, with a time step, you would say, okay, do I see you now? Do you see me now? Do you see me now, etc. And it turns out that that turns out to be problematic in a lot of cases. So I won't get into it here, but since we are modeling it using just these events, and remember, nothing happens in between these events. If none of this happens, then the end move will happen, and everything's going to be fine, because that's the way discrete event works. But now we need to figure out, can we schedule this enter range event? In other words, if we can identify when this start move occurs, can we calculate how long it takes, say, the time to detect from when the target starts its move, not actually the time to enter, not the time to detect, the time to enter. How long does it take between when it starts moving and when it enters the range? And as we saw when we used the equation of motion in our numerical example, if I can figure out when it enters the range, then that, together with the equation of motion, can tell me exactly where it is. Okay, so that's really the first problem on our plate. So can we solve this? And the answer, as you might guess, is yes, because if we couldn't, then I wouldn't be babbling at it for you. And the key thing to recognize here is that at this point, when the target enters this maximum range, it's exactly at a distance r from the sensor. Remember, the sensor is sitting there at the origin, stationary. Again, this is the simplest case. So so now the question is, when is the target exactly distance r from the sensor? And if we can figure that out, then we have solved our problem. So now just by way of a little notation, Remember, we've seen the Euclidean norm thing when we were doing our vector velocity calculation. Another way to look at it is that the square of the norm of the sum of two vectors is the dot product of the two of the sum. And remember that there's a distributive law for vectors even, as long as we use the dot operator for multiplication. So by multiplying this out and using the distributive law, we have a dot A and 2a dot B and b dot B. And then remember that the norm squared is the same as the dot with itself. And so that's a squared plus 2a dot B plus norm of b squared. Again, remember a and b are both vectors here. So how can we apply that? Well, remember that the range, this is how the range of the sensor, this is our equation of motion for, remember we decided that t, I said t is equal to 0 because we're gonna say it starts moving at time 0. That's actually fairly standard because, and that works well with event graph and discrete event stuff, because remember all the delays are from the current time to the future time. So in doing the calculation, there's really no loss in generality of saying let's assume that it's a time 0, because at the end we're going to be looking for delays. Okay, so now how can I unravel this? What are the knowns and unknowns? I know what R is. I know what X is. That's my last stop location. I know what V is. That's the velocity. What don't I know? I don't know T. And that's what I want to solve for. So here's the way to solve it, or a way to solve it is, well, if we square, remember this is going to be a square root here. But if I square both sides, then I can apply this and basically multiply this all out. So this would be the norm of x squared twice the inner product of t, v, and x. Remember, t is just a scalar though, so this is going to be the inner product of v and x. And then finally, when I square the second term, it's going to square the t and give the norm squared of v, which is actually, just incidentally, is going to be the speed squared. Although once we start having both the sensor and target moving, that's not going to be so useful. Okay, so what is this? What do we know? We know this, we know x, we know v and x, we know v. What don't we know? We don't know t. And so what is this? This is a quadratic equation in t. And so it turns out we can solve quadratic equations. I hope all of you can solve quadratic equations. If you don't remember, then just kind of brush up on your algebra 2. So when we solve for t, we get this stuff right here. So what is this? This is minus v dot x over the norm of v squared, plus or minus the square root of all this stuff in here. So this is, again, the norm of v squared. This would be the square of the range minus the location of x squared, plus the inner product squared divided by norm of v squared. So you can actually, if you concentrate on this and sort of think of geometry and remember stuff about cosines and what have you, it's actually, you can actually kind of get the intuition of this. So just as one example, the inner product has to do with how acute or obtuse the angle is between these vectors. And so if my x vector is something like this, and my velocity vector is kind of going like that, then notice that that as vectors, we can actually look like that. So in other words, the angle between them is an acute angle, and the inner product of two vectors that have an acute angle is actually negative. So in other words, if the target is moving toward the sensor, in other words, if the velocity is such that it's kind of working against the location, then this inner product is going to be negative, and so a negative of a negative is positive. So that, how should I say, is like when you look at the negative, we have a bias that makes us look at expressions like this and think of them as being positive. But in this particular case, see if this is what's going on, see the x vector looks like this, but the velocity vector is going to kind of look like this. And so we're going to have an acute angle here. I'm sorry, an obtuse angle. An acute angle would be have a positive inner product. And so with an acute angle, an acute angle would be if it was kind of moving away from it. Okay, so okay, but here's the thing: is that we were looking at the canonical. In our canonical sequence, we started outside of the target range, the sensor's range, and then we cut through it, and then we went to the other side. Now, is that the only possibility? Okay, so first of all, we've actually solved our problem, and our problem was, can we identify what the enter and exit ranges are? Now notice that there are two solutions. And so in our canonical example, we have this plus or minus. So the minus would be the enter range. That would be the smaller root. So the smaller root would be how long what the delay would be to schedule the exit range. The bigger root would be how long the delay in order to schedule the exit range. Okay, so we've solved that, but it turns out that there are just other possibilities. So let's look at all the different possibilities. The first is what we were looking at. Okay, so the first, we start outside, we go through it, and we wind up on the other side. That's in that case. How can we identify that? Well, in that case, we would have two positive roots. See, here's the thing: is that it's important to be able to identify this algebraically. If we can't identify it algebraically, then we don't have any chance of implementing it on the computer, because everything in the computer has to be entered as an expression. And we need to somehow identify what is going on with that. Okay, so let's look at number two. That's labeled here. So number two is the situation where we start off inside the sensor's range, and we start moving, and then we'll eventually leave. We can identify that when we have one negative root and one positive root. Okay, so how does that work? The reason for that is that if we'd sort of been continuing this whole thing, not necessarily starting here, that means that we had entered in the past, that's the negative root, and we will exit in the future, that's the positive root. So when we calculate this expression here, if we get one negative root and one positive root, that means that the enter range was in the past, the exit range is in the future. And so in that case, we would simply schedule the exit range with a delay equal to the positive root. Okay, so here's another possibility, number three. And that's if the target just misses the sensor altogether. Is that a possibility? You know, if you think, just think of what a scenario you might have. Of course, that's a possibility. There's no reason to think that a a mover moving around is always going to enter the range of a sensor. And so in that case, here's our mover, and here's its start move, and there's its end move. But when it starts move, again, we can do this calculation. What will we find? We will find that there is no real roots. In other words, how can we identify that? Well, if we look at what is under the radical here, this expression, with this expression, if that's negative, if the expression under the radical is negative, then we have complex roots. That is, no real roots. And the geometry of it is that the mover will simply miss. In other words, there's no, what is it that makes these two real roots? Well, because we have an intersection here. And likewise here, we conceptually have an intersection. It wasn't drawn very well, but if you just look at this line, then this line intersects the circle. This line misses the circle. We can identify that by saying that there are no real roots. So we don't have an enter range, and we have no exit range. And so actually our recourse is to do nothing. So in other words, when we're trying to figure this out, if we come up with complex roots, that is no real roots, then we don't have to do anything. So that's good news. And then finally, let's look at this situation here. We start outside the range, but then we're moving away. What will identify that? Two negative roots. In other words, what's conceptually, both the enter and the range and the exit range had happened in the past, and we're moving away from the thing. And so again, we're never going to have an intersection. So we do nothing. That's our recourse. So the only times that we have to do anything when we encounter this situation are if we have real roots, one of which at least is positive. And if we have two positive roots, we choose the smaller one to schedule the enter range. We can choose the larger one to schedule the exit range if we want. Or if we had started off inside, then we have one positive root, we can schedule the exit range for that. So what we've done is we have, again, from our simple canonical example, we've come up with an algebraic expression that is the delay between when that start move event happens and when something in between might happen. And then finally, we've identified all the different possibilities. These are the only things that could basically happen. And so now we have a fighting chance, as it were, to model components which are going to detect these movers as they move around. And that will be the subject of our next talk.